Hi there, my name is Innerlight. My creator have been making Kigurumi masks for more than 17 years already, and today I want to talk to you about how to better engineer Kigurumi masks 3D models for 3D printing. The reason for this video, and this video is actually the sequel for my Kigurumi mask durability video, link will be down below, of course. The reason why I decided to do this video is because I was commissioned to 3D print a Kigurumi mask shell made by, the 3D model was made by another artist. Here this the link on Thingiverse, well not the link, the listing on Thingiverse. Their artist is Kapapo Lilia. You can also find her on Twitter, and she is a pretty good, pretty solid mask designer. Though I personally do not like this kind of style of the mask, but I have to admit that design-wise and shape-wise, it's a pretty solid design. So here is the 3D printed mask that I did on my printer, and well, the thing is that as I was preparing this mask to print, I found out that though the design of the mask is pretty solid, the structural design, the engineering, the mechanics of this design is lagging pretty behind, and though the later designs, the newer designs by this artist have some improvements from the engineering standpoint, they are still lack the general engineering knowledge. And today I want to talk to you about how to design a Kigurumi mask shell for the 3D printing, how to make the 3D model. And first of all, that I want to talk is how actually this mask was designed as a 3D printed 3D printed file, the STL file. So the first it was made a low poly mesh of the mask, of the head, without any seams, without any holes, etc. Just the eye holes were in this mesh, and ears were made separately. Well, there are different ways to do. You can make ears separately, or you can integrate them into the mesh itself, the low poly mesh itself. I usually prefer the latter, but actually this doesn't matter much, since in some cases you even may want to have a different ears, different set of ears, so ears can be removable, etc. So you may stick with the idea of having a separate ears. The separate ear mesh that would be just unified with the mesh on the late stages. So there was the low poly mesh, then it was subdivided, as I can see from inspecting the final STL model. It was subdivided by 4 stages, so it's pretty serious subdivision. Each stage is making the polygons, split each of the polygon into 4 polygons, smaller size, so the actual polygons in this 3D model end up to be about a couple of millimeters in length, or a couple of square millimeters in the area, so it was pretty small stuff. And then it was extruded by 3 millimeters to make it 3 millimeter thick, and then there were the mask was split. Ears were unified with the rest of with the head. There were some extra small meshes that were subtracted from the mask, and they became these small slits for eyes for the user to see out. So you can see these small slits, they were the mesh. This stuff was a subtracted mesh, and then the hinge was a separate mesh that was unified with the mask. At this point of view, when I inspected this 3D model, I wanted to remodel it, but it was very hard because it was already in high poly stage, and remodeling it would be basically making it from scratch. And the first mistake that I noticed in this mask is that the eyes, you can see the eyes have pretty small details, and because of that small details, when you make the thickness of the mesh, basically what is the thickness is each polygon became offset by a certain by the normal or to the polygon by a certain amount of millimeters, and sometimes you can make a self-intersection, and inside this mask in the eye area there were those self-intersections. So how do you avoid that? You cannot avoid that straight ahead, but you can get rid of them after you made this shell operation by, for example, deleting some loops of the some edge loops around the eye, so that would just smooth the inside of the mask. And this also made some areas of the eyes to pierce down inside. That was just some unnecessary bumps inside. That was also the remnants of that operation. So the inside of the mask needed to be cleaned a bit, but that's not the biggest problem. The biggest problem with the engineering, well, I have here some failed prints. Well, it was because the printer, it's a bit hot in the summer here, so printer get too hot and it became unstable, so I had this failed print, and it actually became a useful thing. So let's see how it made. So let's walk through the mistake that I found. The first mistake is that it is just split in half. So it just split in half here, and the problem is that when you put the wig on top of the mask, when you open the mask and close it back, you will have some serious disturbances on top of the wig. So you cannot just put the styled wig on top of the mask and then put the mask on. You will have to restyle the wig every time you put the mask on, and this is inconvenient. So you either want to have the split here on the forehead, so you disturb only some bunks in front of your mask, or you want to have this split like here, like this type of split, to disturb just the back part of the wig. So this is basically more convenient. Also, there is the problem that the seam is very close to the ears from the back, from this side, and because of that, the designer had to do these holes. So these holes are supposed to be used for the clasp, and because we cannot place the clasp here, it will be too visible, and we cannot place this clasp here because we do not have the area for the clasp here. We have to move it upper, and if you watched my previous video about mask durability, you know that the higher you put the clasp, the more problematic is it the overall structural stability of the mask itself, because you have that leverage of the mask, and just when it wants to open out, you will have to have some extra leverage, and extra forces will be happen here. And the problem with 3D printed masks in this case is that 3D printed masks have less strength between the layers than the strength within the layer, and regardless of how you orient the mask, you have to orient it like if the layers are horizontal, you have to orient it somehow in this way. So regardless of how you would orient it on your 3D printer, you will have some layers that will have the lines across those holes, and because the strength of 3D printed parts across the layer is way more than strength between the layers, you will have a potential place to fail, a potential place to form some kind of crack in the mask. And the higher you put the hinge, then larger forces will be introduced to the mask, and the top hinge will simply not work at all. All the forces, all the load will be distributed to these clasps, and therefore to that small holes. So when I modified the mask, I didn't modify it in 3D, I modified it after the printing with a 3D pen, with some chemicals, and I will show you how I did it a bit later. So I had to just use those holes with a 3D pen with molten plastic, and move the hinge down here. I had to add some element behind the mask, so you can see this. So you can see this here. I cut it from this part and put it to this part, and put the hinge behind the ears. It won't be visible, but way more stable. Now the next thing that you may notice from this print is that we have these big flaps. The flaps themselves are not a problem. It's actually a good stuff. But you do not need flaps to be that big. You need just about 5 millimeters protruding from the part, and that is perfectly okay. And the other problem is that you have flaps only on the one side, and on the other side there are no flaps. So look over here, we have the mask, we have it closed like that, and though those flaps do prevent mask from moving, the back part of the mask from moving inwards, they have no problem. They let it open very easily to another direction. So you need to make flaps not only from one direction, but counter flaps that would that move back. So basically, this is what I did here. You can see the original flaps. You can see the original flaps here, And you also can see the extra flaps I added here. So the mask in this case, when it closed, it doesn't want to move anywhere. So it doesn't want to move that way, and it doesn't want to move that way. The only way it wants to move is to open and close, and the clasps prevent it from opening by its own. So this is another improvement, the actual improvement that I did with this mask, with this design. The other thing that I want to focus your attention, it was also addressed in the video about mask durability later, is how the hinge is connected to the rest of the mask. So you see the mask is pretty thin, but this place is pretty thick and there is a pretty sharp corner. So what is the problem with these sharp corners? The problem is that when the thickness of the material drops so dramatically, like here, you have a pretty serious concentration of the stress when the mask moves in one side to another, and it became more brittle in these places. So if you watch my previous video, I actually have some videos, some photos here. So this is one of the typical cracks that are caused because of this problem, this particular problem. And to avoid those cracks, you need to smooth out this gap, basically. So this is how you should do this. So this is my previous video. And in this mask, I actually added, so you can see, I added with the 3D pen some extra ribs to smooth that out and smooth them the inside of this. So you can see them. Well, I think this is even better. So you can see also how the thickness is, how it is more thick at these areas, and I didn't add it through all the perimeter. I added it through the corners, and I also added some extra. So you can see the ribs here. Inside, I also added some ribs on the edges here, and I also reinforced the places where the hinges are connected. So the more load from the bolts will be distributed to the thicker material, to more material, and it will stay, well, longer. So you can see also, well, you can see I also added some extra ribs here, also for reinforcement, and I also add some thickness at the perimeter of the mask opening. And here I actually smoothed out all that opening, so it will not tear the header tie. Because when you do just the blender thing, just the thickness thing, you have these edges, the right angle edges here, and that maybe those edges may be damaging, so you need to smooth them out, and you need to add some thickness here and smooth them out. The thickness can be just twice as thick as the rest of the shell, and because you do not need the whole shell to be that thick, and just in some areas. So you also can see the reinforcements here. I added to this counter clasps. So at the bolt area, also to reinforce these elements. So this is the reinforcement of this mask. The other thing I want to tell you about how I treated this mask is about how I treated this mask with chemicals after I added all that ribs inside, and after I added all that hinges and so on. The material I used to print this mask is the PETG. It's pretty solid, pretty durable. Well, not as durable as if you would cast it out of fiberglass, for example, but well, it is okay if you will not try to play football with this mask. But again, let's recall that it is 3D printed, and it is 3D printed on FDM printer, and so it has layers, and as I mentioned earlier, the adhesion between the layers is, the strength between the layers is less than strength within the layer. So I decided to treat the mask with the chemicals, methyl chlorine. In this case, this is the chemical that dissolves the PETG. It can be used as a glue. It can be used as a smoother agent. It's the same smoother agent for PLA as well, but PLA is less stronger than PETG with almost the same printing parameters. So I treated it with this chemical, but I treated it from the inside of the mask. It's important, because when you try to treat it on the outside, you try to have the smooth finished surface on top of the mask, or on top of your part, and your goal is aesthetic. But when you treat it from the inside, the goal is different. You want to melt it a bit with this chemical, and because of how chemical dissolves and how it melts the plastic, it helps you to mix the polymer chains in the plastic between the layers a bit more, and to release some stresses between the layers, because even if PETG have a pretty small thermal shrinkage, it still has some thermal shrinkage. And by applying the chemical to the mask, to this part, you release these internal stresses a bit, and also because the chemical, well, it is pretty easy to evaporate, but it doesn't evaporate at all. It dissolves into the material as well. The chemical that gets to the outer surface evaporates, and the chemical that gets in the other direction dissolves the surface very little, but that is enough to mix the polymer chains within the mask. And because it is pretty thin, you do not have the outer wall and the inner wall are connected. It is pretty solid all the way through, so the chemicals mix through the whole of the mask and make it even stronger. And of course, it's not just because the chemical, but also the direction how you apply those chemicals. You can use the brush, because you do not care about the surface smoothness and how nice the surface looks, but you want to apply the brush. So in my case, I printed it in this orientation, the top in this orientation and the back half in this orientation, and I applied the brush in the direction that is perpendicular the layers. So basically the layers are stacked this way to all the mask, and I applied the brush in this direction to mix the layers some more, to add some rigidity, and to make the mask more isotropic in nature. Well, the other stuff I want to talk to you about is the pretty popular today idea to, well, deepen the clasps in the mask surface so they won't be sticking out, so they get inside, a bit inside, they get deeper, and people usually model something like that. Some cavities for those masks, and you can see then also did did a rib here, did some ribs here, but those ribs are definitely not enough for the purpose. And this is because when you move the mask around, when you transport it, something like that, you can have some loads from the side, from the top to bottom, etc. And because we do not have any ribs here, we have some leverage for the forces. And here it is. From the start, when there are some forces, they can construct like here or expand like that. And the loads are pretty large here in these seams, and this may cause some extra cracks to happen. Basically here and here, or like here, you can get a cracks pretty soon. How to get rid of them? Well, you can see this is the improved design. So we have ribs here, we have ribs here, and those ribs actually makes the sudden loads to go straight through this part, and instead of trying to bend the part, they are just trying to contract or expand the part. So, and contracting or expanding is way more easy for the part to handle than to get bent. So this is also how you need to address these elements like that. So that's it. Again, my contact info. And thank you for watching. I hope that these ideas would be pretty useful to you when you will 3D model your own Kigurumi mask. Again, bye bye.